welcome back. So, last time we started looking at Newton's laws, okay, in the last part of the lesson, and we spoke about Newton's first law, but now we've got to say what happens when the velocity of an object changes. Now, this is a very open-ended question because am I asking you about force? Am I asking you about the effects of a force? Am I asking you about momentum? But of course, we're working on momentum. That's the theme of our lesson right now. So obviously, I'm asking in terms of momentum. Okay? I didn't ask how does the velocity change, because then that would be force. Only forces can change the velocity. So if the velocity of an object changes, that must result in the momentum changing. Okay? You're going to hear this lots. Why? Because momentum is mass times velocity. So if the velocity of an object changes, its momentum must change as well. Let's look at this. So, the issue is this. To change the velocity of an object, we must have a net force. We must, okay? Newton's first law says to us that it will actually stay at constant velocity if there's no net force. If I want the velocity to change, I need a net force. So I need an acceleration. And I'm not saying that means it's going to get faster or slower. It could be either. So we need an F net. Now we're going to develop something here, okay? F net, Newton's second law, is equal to mass times acceleration. Now, before the break, I asked you to keep in the back of your mind what the definition of acceleration is from equations of motion, which you did previously. So now we've got to think about it, and we go, well, acceleration is defined as the rate of change of velocity. So it's how quickly or how slowly velocity changes. It doesn't mean that it's going to get faster, and I'm making a big deal out of this because in everyday language, we use the word deceleration to mean slowing down, and that's fine in everyday language. But in science, we use the term negative acceleration if it's slowing down, because it's about direction. Because if it's slowing down, it means the force is moving against the motion, and that's usually given as a negative, okay? So, acceleration, rate of change of velocity. How do we put this as an equation? Well, acceleration is the rate of change. So it's the change in velocity. Remember, delta, the triangle, delta means change in, okay? So we would have also written it like that, where we have VF, final velocity, minus initial velocity. It's always final minus initial. Now we go, okay, so I know what acceleration is. Now we're going to do a little bit of a maths thing, okay? So I'm going to take this part of the equation, and I'm going to substitute it in there. So I'm going to take the A away, and this means my equation becomes this. Now we're starting to see something that looks a little familiar, because I've got a mass and I've got its velocity, and we know that momentum is mass times velocity. But that's a change in velocity. So actually, I can rewrite this equation again. Okay, so now I'm going to expand it. So instead of delta V, I'm going to put this. Okay, so keep with me. So F net is equal to m Vf minus Vi over delta t. All right, I hope you haven't lost any of you. I'm going to multiply the m in. Okay, so mVf, mVi. Oh, now I'm hoping some light bulbs are going off, because if we look at this, okay, let's do this one. That's a momentum, and that's a momentum. But it's momentum at a specific point. That would be the final momentum, the momentum after the velocity's changed. And that would be an initial momentum. So actually, I could write this again as being F net equal final momentum minus initial momentum over delta t. So my net force would be equal to a change in momentum divided by time. That change in momentum comes about because the velocity changed. Why did the velocity change? Because we exerted a force on the object. So we had an equation that said mass times acceleration. Sometimes we don't know what the acceleration is. We only know how the velocity changed. So we can also say that F net is my change in momentum. We've taken an equation that you knew, and we've manipulated it to get something else that we can use in a different context. Okay, so yes, F net equals ma is useful, but sometimes this change in momentum is actually more useful. It depends on the information we're given. All right? So that gets us to a different statement of Newton's second law. I gave you that nice long one where the acceleration is in the direction of the net force, with the acceleration being directly proportional to the net force and inversely proportional to mass. Yes, long, lots of words. If I write it in terms of momentum, it now says to us that the net force acting on an object is equal to the rate of change, of momentum. And I took that away, that's why. Okay. Oh, why doesn't it want to write for me? All right, we'll get back to that. And it's in the direction of the net force. So, normal Newton's second law still relates to the direction, okay? So you've got to have direction in there. But now, instead of doing all those other things, it's equal to the rate of change. Guys, that word rate cannot be left out here because it's not equal to just the change of momentum. It's equal to how quickly the momentum changes. That's really important to get here, okay? It's not just about the change. It's about how quickly or slowly it happens. So, here's our next equation, where F net equals delta P over delta T. That's our equation. Change in momentum, now I didn't write it like that just now. Remember, change in momentum means that it's PF minus PI. Now, if we go through all the maths again, that means that this is going to be m Vf minus m Vi. I take the m out. I just want you to see that we can write this another way. So we get m delta V. So sometimes you're going to see the equation written as F net equals m delta V over delta T. Now, of course, with it being written that way around, what are we assuming? We are assuming mass remains constant. Okay? That's the assumption we're making. If we look at this, we're saying mass is a constant. So, F net is the net force. The direction of the change in momentum, because it's still a vector, is the same as the net force. Change in momentum, still in kilogram meters per second, and of course time is the time interval in seconds. Okay? Now, we've only considered what happens when the velocity changes. But Newton's second law in terms of momentum is actually very useful for something else. And that is for when a rocket gets launched, okay? So a spaceship, a space rocket, whatever, we launch something up in the air, and we try and work out what the acceleration is. So we go, okay, we have a net force acting on the object, and we go F net equals ma. The problem is the mass is changing. There's, at the bottom, by the engines, okay, there's a lot and lots of liquid hydrogen, lots of liquid oxygen, because they use a hydrogen fuel cell, essentially. There's lots of this gas and liquid that then gets burnt up. That creates the upward force that pushes it, okay? And that upward force actually remains constant. What happens is now the mass is decreasing. So the mass is getting smaller and smaller and smaller in order to help it accelerate. But how can we sort of work that out? Because I can't work out the acceleration here because the mass keeps getting smaller. So the acceleration is actually changing. But if I look at it in terms of this equation, they can actually predict how fast my rocket will be going at a certain time, because this will become final mass with final velocity minus initial mass with initial velocity over time. And the whole point here is that this net force will remain constant. And as the mass gets smaller, the velocity can get bigger. So it helps it accelerate. So when an object like this has a changing mass, Newton's second law in terms of momentum becomes very useful. The first law doesn't help us here because it needs a constant mass, okay? The first statement of it. What I need you to get here, okay? Okay, I've done that, is this. Before we say goodbye for the end of this lesson. There are two statements now that you know for Newton's second law. You must still know both, okay? This is what you've got to be paying attention to when you read your exam. If they just say, state Newton's second law in words, you can use either statement, okay? So you can either go, when a net force acts on an object, the object will accelerate in the direction of the net force with an acceleration that is directly proportional to the net force and inversely proportional to the mass. Or you can tell me that the net force acting on an object is equal to the rate of change of momentum in the direction of the net force. Doesn't matter, because they've said Newton's law, second law general. However, if they want the momentum statement, they are going to say to you, state Newton's law in terms of momentum. If you don't give the one with the rate of change of momentum, they're going to give you naught, because you haven't answered the question. They may, though I haven't seen it very often, say, state Newton's law in terms of acceleration. Then it's the long one. Okay, so please don't go, I'll learn one and not the other. You must know both, because they'll be asked in different contexts. Okay, so if they're going to ask Newton's second law while busy with a momentum question, they'll want it in terms of momentum. But of course, it's a section on its own with Newton's laws. Okay, lots to think about. Think about how we got to the equation And in the next section, next part of the lesson, we're going to look at some application. So I'll see you in a couple of minutes.